Big thank you to everybody that's on the call today, both the members of the EEFIT team, and they'll be introduced very shortly, but also to everybody listening and spectating. So thank you very much for giving up your time here. I think it's going to be a very packed hour and a half, so I won't waste any more time. This evening's lecture or presentation is around the EEFIT mission to the recent Haiti earthquake. Mike, the team leader of the EEFIT mission, will introduce the event or the earthquake, the team and the mission itself. Just a little bit of housekeeping to say that any questions that you have, please post them at any point in the chat of Zoom here, and then at the end we'll take all the questions together, okay? And also to say that EEFIT is the Earthquake Engineering Field Investigation Team, which is a team of built environment professionals, both academic and practicing engineers, who visit the sites of disasters in the immediate aftermath or investigate disasters in the immediate aftermath to learn the key lessons that are pertinent to our and related sectors, and disseminate those learnings. And that's exactly what today's today's presentation is about. EEFIT is supported very much by the iStruct, and we extend our thanks very much to the institution. And also to our sponsors, which will be listed in 2 slides' time. For anyone that's interested in joining EEFIT, then please do look up EEFIT, iStruct, and get in touch about joining. So with no further pause, I'd like to hand over to the team leader, Mike Whitworth, who will begin the presentation. Thanks, Mike.
Yeah, thank you very much. So without further ado, just as an introduction, I'll provide sort of an introduction to the project and the structure of the EEFIT mission and how we link them to the overall EEFIT mission and their objectives, before I hand back to Josh to provide an introduction and some background into some rapid building assessments that was undertaken directly after the earthquake, which forms part of the introduction to our data collection, which then feeds in to handing over to Tracy from Steer, who will be covering the background of the data collection, which formed quite a heavy basis of our remote mission. Camilla and Mobin will then cover the characterization of the event with Matab and Valentina covering some remote sensing analysis, and then handing over to Luigi, who will introduce the team who led a large package of the work undertaking the damage assessments based on the Steer data collected. And then I will draw it together for some concluding remarks. So just a little introduction to the team. I won't go through everybody on the list, but it was, as you can see, it was brought together from a wide range of academia and industry and global coverage, which is really nice to see. And I'd also like to do a shout out, and Tracy will touch on this more, to the people in Haiti who collected and really almost led this mission in collecting the data for us going forward. And last but not least, I'd also like to just thank our corporate sponsors who, without their support, EEFIT missions in the real world wouldn't be possible. So just looking at the impact as a little bit of an introduction. So the earthquake happened on the 14th of August at 08:29 local time. It was a magnitude 7.2 earthquake, and it struck just off the Tiberian Peninsula in Haiti. At least 2,000 people lost their lives, with over 15,000 injured, and over 130,000 homes were damaged or destroyed, with a significant number of people being displaced. An estimated $1.6 billion worth of damages and losses were estimated both based on the post-disaster needs assessment. And coupled with that, the situation within Haiti is complicated both politically, socio-economically, with an example being the assassination of the Haiti president in July. And then also on top of that, the earthquake and the recovery effort was compounded by the hurricane that followed through on 2 days later. So the situation in Haiti is extremely complex, which impacted both the recovery effort and the assessments on the ground. So looking at the EEFIT objectives and how we structured the event, the mission, it was key to acknowledge that we were not going to be able to assess all the key EEFIT objectives. So we structured the mission firstly to try to understand and characterize the event, looking at geological and seismological data. And then one of the things we were interested in as a team was how remote sensing, from a remote mission point of view, about how remote sensing analysis could support us in undertaking a range of different assessments. So we've used this as a study to try to understand how we can support rapid assessments and utilizing some of these techniques going forward. And then that all fed in through the STEER fulcrum data set, which Tracy will talk about, looking at how we could assess remotely different building damages and come to some conclusion about those events, with the aim of looking at the interlink between these different assessments and data sets. So without further ado, I'll hand over back to Josh to run you through some of the earlier building safety assessments.
Thanks a lot, Mike. And can you hear me now?
Yes.
Good. So to give a little bit of context before we dive into the EEFIT and STEER findings, I just wanted to give a little bit of information of the initial building safety assessments conducted in the initial days after the event occurred. If you wouldn't mind going to the next slide there, Mike. SARAID is a UK charity, stands for Search and Rescue Assistance in Disasters, that deploys to overseas disasters primarily in a search and rescue capacity. But for Haiti, then we deployed a 6-person team to assist with damage assessments, or rather damage assessment coordination, under the direct request of the Haitian ambassador to the UK. That 6-person team was Rob Davis, Will Selly, Nick Pogue, Susie Cooper, Giles Whaley, and myself. And what we did was, or what the team did was work closely with the Swiss embassy, or rather engineers of the Swiss embassy and engineers of the EU civil protection mechanism, to support the Haitian authorities in set up and run their own system of damage assessment coordination, something called a damage assessment coordination center, which has precedence in previous events in Albania, earthquake of November 2019 and the Beirut explosion of August 2020. If you go to the next slide there, Mike. So I think the audience of this presentation would understand the need for safety assessments or building damage assessments, but Mike mentioned some numbers there. He mentioned 137, I believe, households destroyed and damaged. Of course, those kind of numbers didn't exist in the initial days, right? So in terms of understanding the scale of the issue, that's where a rapid screening of the numbers of damaged buildings is very important. Many of those damaged buildings would have been health facilities, schools, aggregation points such as areas of worship, which are very important because they also double up as hurricane shelters, and this occurred during at the beginning of the hurricane season. So you have a number of people that have been displaced, and the question immediately on the mind of members of the government will be, how do we get people back into their homes? How do we get people away from unsafe buildings? Should hospitals be evacuated? Which parts of buildings can still be used? And similarly for other buildings as well. If you could go to the next slide. To give that a bit more of a kind of human context as well, we'll talk a lot about data and numbers, but I think context is important. And this is an example of one hospital that was quite close to the Lekai civil protection kind of headquarters. So Lekai is a city in the south near the part of within the affected region, and I think that'll be demonstrated in the coming slides. This particular hospital had between 30 and 50 patients located outside the hospital on the concrete outside, essentially. This is actually about 10 days or so after the earthquake, and many of these people outside were in very bad shape, many of them being actually people that were injured during the earthquake. A preliminary assessment suggested that the building had not been structurally impaired by the earthquake. So there was not damage there that indicated that the structural load-bearing capacity of the building had been reduced. But then the question of, okay, how do you then get those people back into a potentially functioning hospital and off of the concrete? If you go to the next slide there, Mike. And that's not something that would be within the jurisdiction of an international team, and nor should it be. That would be the remit of the government, and that's why Damage Assessment Coordination Centre is very much focused around capacity building of the host nation. So the acronyms, etc., here are not too important, but on the bottom left is a list of the local actors that were key in building and continuing the Damage Assessment Coordination Centre after the international mission had finished. And that table at the top outlines some of the key considerations that had to be agreed and worked through with those key actors on how that Damage Assessment Coordination System would be undertaken. If you go to the next slide there, Mike. And this is my last slide. So this is, again, just some examples of some of the things that were needed to be agreed on what would and wouldn't be assessed, how that would be conducted, who's doing the assessments, whose jurisdiction, how's the data being managed, so on and so forth. And this is all to provide that context of, yes, we're going to look at a lot of data, but let's not forget at any point that we are talking about a lot of people who's lost their lives and livelihoods. And the information that's actually being disseminated by the team here is of relevance to this and future disasters. So please do keep in mind how we can make use of this information in the future. And these assessments, I won't go into the numbers and the details because the next slides will do that very amply. But just to say that this is one of a number of different assessments. So this was setting up building safety assessments. In the initial days that were led by that bottom right-hand side list of acronyms. The MTPTC is the Ministry of Public Works, so they led that particular side of things. It dovetailed into a kind of much wider, longer-term set of assessments that were being partly funded by the World Bank and other donors, led by the IOM and carried out by Miyamoto International, a large consultancy firm, etc. And that, of course, also related to the assessments that STEER are conducting, and of course the collaboration that's then enabled with EEFIT here. So these assessments are all very key, and I'm keen to see how we could use this information for this and future events. Thank you very much, and with that I'll hand over to Tracy to discuss the STEER assessments. Thanks.
Great, thank you, Josh. So what I wanted to do is just step you through a little bit of how we propped up this local data collection effort. Inevitably, in places like Haiti, we often lack access to skilled engineers that we can mobilize to conduct the kinds of assessments Josh was alluding to. And this is a problem pervasive across especially low and middle income countries. Compounding this was the security situation we were facing in Haiti after the earthquake that made bringing in extra personnel from outside something that a number of agencies and NGOs were not in a position to do. So as a result, we seized an opportunity. The quote on this slide just basically speaks to the fact that there is a possibility to paraskill an assessment such that you identify the parts that need to be collected or completed in the field, and you identify other aspects that can be conducted remotely. And this has some interesting capabilities in settings like Haiti, and we were able to use that in this event. Basically, smartphones were pervasive in this setting, and we were able to create an app on a commercial platform called Fulcrum, which meant that they could conveniently go into the App Store, download this same app, and synchronize almost immediately a customized Creole mobile application to use in data collection. You can see a group of Haitians here. These are non-engineers who basically became the agents in their communities for documenting and self-reporting damage throughout the affected areas. So I first just want to applaud them. Many of these individuals were displaced themselves, and they were out there collecting data that we ultimately could benefit from. Next slide. So just a little bit about how we introduced a sampling strategy for them. In this particular effort, we did not have the budget and the mandate to assess every structure. So we actually were going through a sampling strategy that would avoid us biasing only structures that were damaged, but also not commit us to evaluating every structure. So we have a 3-level sampling strategy that's described in this slide. Essentially, at the first tier, the yellow bar is an unbiased sample taking every third building. So the assessors would be directed to a geographic area of interest for the day. They'd be instructed to sample every third building on their segment of an assigned road using what we call the Steer Rapid Response app. This is an app that's open. Anyone on the call here can have access to the app and the data. Then we had 2 exceptions built into that protocol. Exception number 1, if they came across what we called a priority building, this would be a building that was likely built by an NGO using a standardized floor plan, such as a Food for the Poor house shown in one of these images here. Then they were asked to include that regardless of whether it was the third building, because we did want to document how designs that had some level of oversight in their production and execution ultimately performed. We also asked them to always document any critical community building, schools, medical facilities, assembly buildings, government buildings. So that every third structure sampling still had these opt-outs to make sure these very important structures were captured. We also asked them to identify benchmark buildings. Eventually, our effort was expanded with the support of USAID and USGS to include a Did You Feel It survey that we're going to use then to be able to get an appreciation of the intensity of the event across the affected area. So they were also instructed that when they saw a benchmark building, these were defined as buildings that were engineered or semi-engineered construction. They were to not only conduct their structural assessment, but also acquire a human subjects interview using a Did You Feel It app. And that allowed us to then correlate the human experience of that earthquake with the performance of the structure and map that back to the various products that USGS has built out around the Did You Feel It surveys that they run and execute for things like Pager and other tools in their arsenal. Next slide. So a little bit about what our non-experts did. In the field, we had just 2 engineers total on our team. The rest of our surveyors, 50 plus, were all non-experts. Some were builders, but most were not having any background in construction. So what they did is they used this Fulcrum mobile app, and I have 3 screen captures here just to show you what they were asked to do. Step 1, they were asked to geolocate themselves on the map and mark the building that they were assessing as best they could. GPS being quite a challenging thing in Haiti, especially once we started losing cell towers due to gas shortages. But they would first mark location as the first step in this first screen capture. The second step was to provide essential building information, name of the building, name of the commune and locality where they were working, the street name if known, and most importantly, what the building was used for, the occupancy. The next step then is to then acquire photos. They were instructed to take photos from all 4 sides of the building, if accessible, and also to be able to zoom in as best they could to capture up close pictures of any levels of damage they could visibly observe. So they were essentially capturing pictures. And then the last step, there's a little microphone icon you'll see on the 3rd screen capture there. They were invited to audio record any additional information about the performance of the structure in the event. We could then use that data for additional context. Next slide. On the back end then, that data is coming into our centralized dashboard in Fulcrum. The screen capture shows how it appears on the backside. You'd be able to see a pin on the map and the information populated by that person using their mobile phone. If there's good connectivity, that synchronizes immediately. Next slide. Then what we do is we have folks on the US side translating the audio files into an English language transcription to take that additional context and populate the box shown in the second image there to tell you what that audio file was saying. Also, we were doing quality control to adjust geolocation and other parameters of the records on the backside, and that was done in the US. Next slide. At the 3rd step, then we were able to then push the records back out to experts who could then assess the records and assign damage ratings, as well as assign the type of construction or typology that they observed, as well as any other notes describing the performance or level of damage that they witnessed. The idea here was to capture the data before it was disturbed and eliminated through cleanup efforts, and then be able to move the records through this workflow progressively so that, again, experts operating outside of Haiti could remotely access the data and enrich it. And that indeed was a vital function provided by EEFIT in this mission, as well as other volunteers who continue to work on the data to this day. Next slide. In terms of the way that we organize the assessment, we wanted to be able to provide some guidance to as best as we can, and we know this is a tricky endeavor. We were trying to standardize the ways that people would approach classifying the construction as well as its performance. Noting as well that not every engineer who might be supporting our effort had a background in Haitian construction. So our typology classifier and damage rating system was mapped to two primary materials that we expected to see in the affected areas: masonry-based construction, which includes any kind of concrete implementations, and then timber-based construction. And then we broke those down into the two load paths that we would expect to see, whether those be infill frames or load-bearing walls, or on the timber side, whether they were sheathing or infilling that timber construction. And then we further customized the guidance to then step through, and as you can see by the two screenshots on the governing instructions given to our assessors, help them understand how we would first classify each of these primary systems into their specific typologies, and then how we would recommend the evaluation of damage, assigning an equivalent EMS 98 scale to map undamaged full to complete collapse along this 5-point scale. All of that guidance was prepared, and we developed instructions in both English and Creole, and made this as well as some training videos available to help our assessors. Next slide. The overall effort proceeded on this timeline. So we have the event on August 14th, and we were collecting data in SUD as early as the 20th of August. And that continued to expand with a collaboration with Geohazards International, who began work in NEAP on August 30th. And we continued to push that data out and expand and expand. By September, we had USAID and USGS partnering with us to expand the effort, allowing us to add more assessors. Eventually, by September 28th, get Grandons into the portfolio, and then be collecting in all three departments data in parallel for the next few weeks, wrapping our mission up around the time that EEFIT was doing its mission week. So by the end of October, we had completed at least 5 weeks of data collection in 3 affected departments. What you'll also see at the bottom of the slide is just the total data counts. In our STEER rapid response app, which is the primary structural assessment, we have over 12,600 records. And in our Did You Feel It human subjects surveys that are linked to specific buildings in that portfolio, we have another over 1,800 records acquired. Next slide. The data summary geospatially is shown here. So you can see a heavy emphasis in NEAP, where we were focused in the epicentral area through the work of Geohazards International. But we did try to reach all major communes and especially city centers in the affected areas, including a detailed sweep around the one instrument in St. Louis du Sud in the south that actually recorded the ground motions through the USGS efforts. Next slide. And a breakdown of the data summary, you can see a heavy emphasis on housing as the primary part of the building inventory. We also have a healthy population of schools, which was a primary focus for Geohazards International. We were able to benchmark schools that were constructed post-2010 with seismic considerations, as well as a number of structures constructed post-Matthew. So we'll be able to evaluate performance for these most recent interventions in improving seismic and hurricane resilience in the country. I will add again that all the data is available to anyone on this call who would like access. You can see a website there that allows you to reach access, and we can provide you with credentials to get in the full back end and experience and interrogate the data yourself if you like. So with that, I believe it's time to hand it off to Camilla, who will take us through the next steps in this webinar.
Thank you very much, Tracy. That was brilliant. Right, so I'm going to talk a little bit, I suppose, taking a step back about the tectonic background for this event, and also thinking a little bit about the work that had been done on this earthquake from a tectonic perspective prior to the mission starting. And then Mobin's going to talk a bit about strong ground motions. Next. So this is a map of Haiti's location. Haiti forms the western half of the island of Hispaniola in the Northern Caribbean. And the reason why we have earthquakes here at all is actually because of the collision of the Caribbean plate to the south here with the North American plate. And that collision is occurring at about 20 millimeters per year in an east-northeastward direction, shown by the black arrow at the bottom of this picture. And so what you can see here is that that collision is highly oblique to the plate boundary in this region. And what that means is that as well as lateral strike-slip motion, we also have compressional motion occurring across Hispaniola. And the way that this is taken up in terms of faults is that there's partitioning. So we have 2 thrust faults, one to the north of Hispaniola and one to the south. And then on the mainland of Haiti, the main faults are 2 major strike-slip faults, the septentrional fault in the north and the Enrico Plantain Garden fault zone in the south. And the region that we're going to focus on primarily today is this EPGF, which particularly in the region shown in the red box here. Next. So if we zoom in on that region and plot the earthquakes that had occurred in that region up to 2010. The small stars here represent the instrumentally recorded earthquakes, so not terribly many of those, but there is a record of several major earthquakes occurring in the 19th and 18th century. And those are shown by the large green stars here. And essentially what I want to show here is that based on the felt reports, those had all been assigned to be associated with this EPGF structure, which is shown by the black line cutting through here. And so our understanding of how the hazard worked in southern Haiti was that there was potential for large earthquakes on what was thought to be basically a quite simple but major strike-slip fault running along the southern peninsula. Next. That was until 2010. On the 12th of January, an earthquake occurred near Port-au-Prince, causing an enormous number of deaths. Over 200,000 people died, and with financial losses equating to 130% of Haitian GDP. So this was a major disaster. Our initial understanding of the earthquake, based on its epicentral location, was that it was again likely to have occurred on the EPGF, on this major strike-slip fault. However, as the aftershocks shown in orange here kind of hint at, and as ground surface displacements shown in the next slide demonstrate more clearly, next, and what was going on here was actually a bit more complicated. So it turned out that rather than being a purely strike-slip fault, about a third of the motion in this earthquake was actually compressional, and rather than being on a vertical fault, it had occurred on a dipping fault instead. And this is important in terms of how we understand the hazard in Haiti, and also in terms of how we understand the tectonics. In terms of the hazard, firstly, the fault hadn't previously been recognized, and it's blind, it doesn't come to the surface, so it would have been difficult to know about in advance. And then secondly, if we think that we can have compressional motion on a more shallow dipping fault, then what that means is that there's a wider area directly above the fault plane, which might be slipping. And that affects how we would think about the potential peak ground accelerations or motions that buildings in the region might experience. However, what we see if we go to the next slide on the hazard map, which was produced after that 2010 earthquake, is that the focus was still very much on the EPGF as the main source of seismic hazard in the region. So you can see there's a kind of narrow concentrated band of high peak ground accelerations along a linear feature, which is this EPGF in the southern peninsula. And this is showing that even in the kind of 1 in 2,500 year earthquake, we're not really accounting for the possibility of that compression occurring off fault. So an important question is this the right way of understanding the hazard in southern Haiti? And this brings us to the 2021 earthquake on the next slide. So on the 14th of August, as Mike mentioned, at about 8:30 a.m. local time, a magnitude 7.2 earthquake occurred to the west of that which had occurred in 2010. I should say 7.2 makes it about double the amount of energy released that was released in the 2010 earthquake. And if we look at the aftershocks on the next slide, we can see that, again, there's this kind of spatial separation with the orange aftershocks associated with the 2010 earthquake concentrated further to the east, and those following this earthquake concentrated further to the west. And I should just mention briefly that these aftershocks following the 2021 earthquake were collected, or we know about them primarily through a citizen science project where seismometers were deployed across Haiti. And that was very important because prior to 2010, there were actually no seismometers in the region. And so that's been one of the reasons we're able to interrogate the strong ground motions here. So again, as in 2010, we see that the epicenter is close to this Enrico Plantain Garden fault. And so the initial reaction again was, oh, this is probably, you know, a major strike-slip faulting earthquake on this very mature fault through this region. However, it transpired again, based on the seismology, that in fact this was an oblique fault rupture, and it had occurred on a fault which dipped to the north, which is the opposite sense to dip that had been mapped on this major fault prior to the earthquake occurring. Next. So based on the ground displacements recorded by radar, which Valentina and Mata will talk more about in a moment, the USGS does a preliminary inversion for where slip has occurred at depth on a fault plane. So this is just a surface projection of a dipping fault, looking and showing that there's about 3.5 meters of slip in this region. And the important thing I think here from an engineering perspective is that when we're looking at a magnitude 7+ earthquake, as the one we've seen here is, it doesn't really make sense for us to think about that earthquake location purely in terms of its epicenter, shown by the star, because what we're actually seeing is rupture over a length of perhaps 70 kilometers, and also extending to greater depths and distances away from the fault. And if we look at that slip distribution in profile on the next slide, then what we can also see is that now we're showing also contours of when the rupture front reached specific points. And what that shows us is this earthquake also propagated from east to west. And that's again important in terms of understanding the ground motions that have affected buildings in the region. So I'd like to leave you by saying that it seems that there's more work required in terms of how we understand what the faulting that's actually going on in Haiti is. And in particular, to emphasize the kind of cartoon on the right here, demonstrating that as well as the strike slip motion shown by the circles, and which has kind of long been recognized in this region, we also have to be thinking about dip slip motion, which might lead to broader regions moving or different expectations of the ground motions that might happen in these earthquakes. And now Mobin is going to talk to you about what those ground motions actually were in this earthquake.
Thank you. This slide shows the peak ground accelerations as modeled by the USGS. It gives us an idea of the intensity of shaking in the earthquake, in the region due to the earthquake. Starting from the epicenter, the PGA is highest at around 0.8 G, moving along the fault from east to west, reaching around 0.5 G towards the end of the 70 kilometer or so rupture length. North, the PGA is around 0.5 G, and towards the south, a slightly lower PGA of 0.46 G is shown, with lower values at the southern coast. Note, local soil amplification effects may not be captured by this model. What's also shown is the single recording station R50D4, which captured good quality strong ground motion data. Next slide. Here, the acceleration time histories are shown. It's noted that the ENN direction is a PGA around 45% greater than the ENE direction. Also shown as the Arius intensity. It's clear this is a long duration earthquake, and with horizontal Arius intensity in the 2 meters per second range, there is potential for triggering severe landslides. Next slide. Here is a map considering the potential near-field zone per the ASCE 7 code. Considering the 15-kilometer band from the region of rupture, it indicates that this region of Haiti could mostly be considered a near-field zone, and this should influence design. The station record is just over 15 kilometers away, and so might be considered as a suitable far-field record for a code comparison. Next slide. It's noted, considering velocity data, a pulse indicating potential directivity can still be found in the record. Next slide. This slide considers the response spectrum of the recorded event and compares it with the Haiti 2012 code, which follows ASC 705, so from 2005. A comparison is also made to the more recent ASC 716 code from 2017. Although most structures in this region are not following code-based design, and if designed would be for good detailing practice or simple design rules, this attempts to determine whether the code-based response spectra remains suitable for design, noting this is the only suitable record that could be used for comparison that may be considered close to a maximum credible event. From this assessment, it shows the code response is fairly representative, though we have exceedance at low periods of the MCE for the 705 code. This is to be expected as the code considers the median response times 1.5. The 716 code, based on uniform risk, considers the 84th percentile, around 1.84 times the median, and more recent knowledge. For many low-rise structures in this region, the horizontal elastic period range of interest is around 0.2 to 0.4 seconds. For non-ductile structures, this could be very significant. However, it's clear that severe damage, so no collapse, could be designed for. For the vertical response, there is significant amplification in the 1.5 second period range. Next slide. Finally, in this slide, we considered the newly available ground motion data for this record, for this earthquake, and did you feel it survey input to see how well it would fit in existing GMPE. What can be seen is a good fit, though some overestimation in the did you feel it records. This could mean that this GMPE is suitable for use in hazard analysis in this region. Next slide, where I'm now going to pass you on to Mahtab and Valentina to present remote sensing analysis.
Thank you. In this part, we are going to cover mapping of the displacement induced by the earthquake on larger scale using INSAR, and also mapping of the secondary hazards after the earthquake, like landslide, and as well as damage assessment, all by using remote sensing data. Next. SAR is an active imaging system which sends and receives signals along the line, which is connecting the ground surface and the satellite, and which is called a line of sight or LOS. It basically measures the distance between the ground surface and the satellite, and also the time of acquisition. So with having two radar images of the same area at different times, we are able to measure the component of surface displacement along the line of sight direction from the phase difference, or let's say from the distance shift between the two signals before and after the event. Next. Interprogram is one of the main products of the INSAR technique, which shows phase differences between two radar images before and after an event. And here, for each acquisition geometry, I mean ascending and descending, one co-seismic pair, including two Sentinel-1 SAR images before and after the earthquake, were processed to generate the interprogram maps. But what we can basically see from an interprogram is color cycles. Each color cycle corresponds to an interferometric fringe, which indicates a movement equals to half of the sensor wavelengths. So for areas with, let's say, very close fringes, for example, here areas around the epicenter, we have greater amount of displacement, as shown on the next slide. Here we see two displacement maps which are obtained by unwrapping the phase values of the generated interprograms, in which the positive values, which are shown in blue color, represent movements toward the satellite, while the negative values, which are shown in red color, represent movements away from the satellite. The displacement map induced by, obtained from the ascending track shows a range from, let's say, minus 40 centimeter to 40 centimeter, and also the descending one shows a range from minus 20 to 40 centimeter. Next. Here we see the coherence map, which is another product of the INSAR technique. The coherence map, let's say, is a measure for the amount of correspondence between two radar acquisition. When the scattering objects on the ground surface do not change significantly, then the SAR signal is considered coherent in time. Coherence values range from 0 to 1. In which the lower value, which are shown here as, let's say, dark pixels or black pixels, represent changes on the ground surface. So based on the coherence map, we are able to get information on the areas with changes after the earthquake. For example, areas with damages after the earthquake. But it does not necessarily mean that all the dark pixels that we see here are only related to damages, because we have also vegetated areas which change very fast over time. And another interesting point here is that we can see a kind of discontinuity in the middle of the coherence map as a dark line. If you see the coherence map, you see a kind of dark line, which on the next slide, you see that this dark line, let's say, perfectly overlaps with the fault line of the 2021 earthquake of Haiti. So that this kind of information can also be obtained based on the coherence data. Thank you. I'll hand over to Michael, who speaks about landslide mapping.
Thank you very much. So one of the things directly after the earthquake was the report of the impact of landslides on infrastructure and damaging roads impacting the recovery effort. So one of the aims of the EEFIT mission was to investigate the use of open source optical imagery based on Sentinel-2 to look at the landslide distribution and evaluate the impact these landslides had following the earthquake. On the left-hand side of the screen is an image, just a snapshot of one area before the earthquake, taken about 2 weeks before, along a river valley, just to the end of the slip motion that was shown in the previous images. And from this, you can see that there's quite a significant scarring on the landscape, showing sort of historical rainfall-induced landslides. And then on the right, on the 14th of August, was a range of landslides that were triggered by the earthquake. So one of the aims of the assessment was to see whether we could automate the system. Due to the number of landslides that were identified, we looked to see whether we could automate the system using GIS and remote sensing techniques to try to see if we could extract them from the landscape using optical change. So on the left-hand side is an image trying to highlight the landslides of the same snapshot using near infrared to try to make the landslide stand out. And on the right-hand side, this is an automated process to try to classify the areas of the landslides to try to identify them, and therefore be able to use it as a methodology to extract it landslides for a wider period, for a wider area. But what you can see is in this large white area and these fringes of blue and grey is actually picking up cloud cover, which means that actually it has a similar signature to many of the landslides that have occurred within the landscape. So this caused a problem with an automated system of trying to identify the landslides and extrapolate the observations to the whole of Haiti to try to identify a wider distribution. So with the support of colleagues at the University of Houston, they undertook some INSAR analysis, looking using the amplitude ratio, which was discussed in the previous slides, looking at try to highlight to see using INSAR, which can penetrate clouds, to see whether we could identify a range of landslides. And on the left-hand side is basically a training method where we've looked at the same area to see, and in the polygons here in pink, to try to extract the individual landslides to see how they can correlate to the INSAR assessment. So what we're going to be doing going forward is using the INSAR to help us identify from imagery that doesn't have clouds, so after the rainfall and hurricane season, to try to use that to train the system so we can identify the full distribution of landslides. Already to date, we've identified over 500 individual landslides within a small cluster of the area, and we expect this to increase when we expand the analysis. Now I'll hand over to Valentina, who will run you through how we've used remote sensing to support our building damage assessment.
Thanks a lot, Mike, and good evening, everyone. Well, following up on the remote sensing analysis, one of the other objectives of this part of the mission was to evaluate whether we could use the remote sensing data to characterize the geographical extent of damage caused by the earthquake, and also evaluate whether this data could be used as a guidance tool to identify the areas that were most likely affected by the disaster. For example, in this slide, we see the distribution of building damage based on the analysis of optical satellite images developed by a couple of organizations that are the UNOSAT UNITAR and the Copernicus Emergency Management Service. And basically the analysis based on the optical satellites was performed for several locations of interest that correspond to the blue and green polygons that we see in the slide, and across the 3 departments that have been mainly affected by the earthquake. For each of these locations, basically the analysis consists in the comparison of the optical images acquired before and after the earthquake in order to identify the structures with visible damage. what we can see that is for the total of the analyzed areas, basically the optical base assessment has identified about 1,800 buildings with visible damage, with dam structures observed up to 80 kilometers far from the epicenter of the main shock. In the next slide, we see that for most of the regions analyzed in the previous slide, the optical base assessment has also captured some damage and obstacles on the roadway infrastructure, and several landslides and rock slides in the southwest, mainly between the urban areas of L'Anglais, Chardonnay, and Port-Saint-Mend. And also several flood events have been observed in the north between Coreil and Pestel near La Sille, nearby the epicenter of the main shock. In the next slide, we see a bit more in detail what happened to one of the locations that we saw in the previous slide. So we are now looking at the area of Cavillon, and the optical base assessment basically has identified two obstacles on the National Route 2, which is a primary road that links the South Department with the Nipis Department located in the northeast of the map. And visual comparison of optical images acquired before and after the earthquake has shown that in both locations where obstacles were detected, basically the damage the roadway has been damaged by the occurrence of some landslides. Another remote sensing product that we see in the next slide that can be used to basically assess the extent of damage caused by the earthquake is the damage proxy map produced by the area team of Jet Propulsion Laboratory of NASA in Caltech in California. And basically, this map is generated by processing synthetic aperture radar images acquired by Sentinel-1 satellites before and after the earthquake. And the concept behind the map is to compare the coherence of a pair of images sandwiched in the earthquake with the coherence of a pair of images acquired before the earthquake in order to target the pixels that experience a drop in the coherence values of the coseismic pair. This pixel, which corresponds to the yellow, orange, red pixel in the slide, basically identify the areas that are more likely affected by the earthquake. And the color variation yellow from yellow to right indicates basically an increasing level of change of the surface that basically is associated with a potential higher level of damage. And some of the locations basically for which we observe a positive signal in the damage area proxy map were analyzed in combination with some earth photos acquired by drones after the earthquake. And in this slide, basically we see in the area of Cavillon, located in the South Department, that the damage proxy map capture very well the damage of some structures, but also some big cracks of the ground. In the next example, the damage proxy map in the next slide has been evaluated in combination with some results of the optical assessment that we saw in the previous slide, and drone orthophoto acquired over the area of Cavillon. And what we see that overall, basically there is a good correspondence generally between the pixels that show a positive signal in the damage proxy map and the structures identified as damaged by the optical assessment. And in the pixel on the right, we see a close-up to one of these locations for which basically both data sets were identifying like a location that should be like a flagged location that might be actually damaged. And we see that both data sets basically managed to identify the actual damage of a church, highlighting how this technology, this remote sensing product, could actually have the potential to be used to target for field works in the emergency response. And so thank you. And now I would like to hand over to Luigi that will go through an introduction of the damage assessment.
Yes, thanks, Valentina, and good evening, everybody, to all participants. So now we'll move to the section that builds on what also Tracy has been presenting through the STEER database that was made available to this virtual mission. And as you'll see, we have been assessing different type of structural system. In particular, we have been assessing, as shown in the next slides, hospital, schools as critical facilities that are very important for rescue operation and also for the operation of the communities, but also we have also focused on churches that can be used as shelters or as systems that as structures where people can be allocated after major natural event. And you see on the right side of the slide also the percentages of the buildings that have been surveyed. Of course, these numbers refer to when this mission took place, i.e. during October, and in fact, we had most of the hospitals surveyed. We are here making reference to what were called also by Tracy as a non-expert data collection. So the team that also is going to present this data in more details later has looked at how this system have behaved, and we have surveyed nearly 82% of the hospitals, 92% of the school, and that will be presented also to case study by my colleagues, as well as churches and housing. For the last two, you see that the numbers are, the percentages of the surveyed buildings are less, and in fact they've been collecting more and more data so the data set has been populated later after our cap date that we have used for the assessment. What I'm going to show in the next slide is also the type of metrics that we have utilized, and we made reference to the damage scale as stated in EMS 98 that has 5 different grades for assessing the damage, moving from the DS1 corresponding to no visible damage up, and you'll see also on the slide a typical intact structure, and then we'll be looking at the increasing damage up to partial or total collapse, and we have been considering, as shown also on the next slides, different structural systems, moving from those that have been also identified as taxonomy in the STEER database, i.e. the reinforced concrete structure, the confined masonry, and reinforced masonry and reinforced masonry. But what I'd like to stress, as my colleague will also show in the next few slides, is also typical type of construction that were found, that were identified there as vernacular structure. In particular, the type of roof is very important, and my colleague will explain more in details also how the mass has played a role. And with this, I will hand over to Alessandra, who will be presenting the results for the hospital buildings.
Thanks, Luigi. So 78 hospitals out of 96 have been assessed by the EEFIT team, and we can observe that 63% of them are reinforced concrete structures, whereas a total of 27% are made of masonry, and only 4% of buildings are made of wood. Some first overall conclusion can be drawn. Approximately 15% suffered extreme damage from partial to total collapse. 6% of them are located within a circle of 10 kilometers from the epicenter. This map actually illustrates the distribution of partially or totally collapsed hospitals along with the epicenter location. We can already notice that there is a path close to the fault line. However, more exhaustive conclusion can be made with the higher number of available surveyed buildings, regardless the structure used. The next slide shows the distribution of the damage grades for the assessed buildings. It can be noted that 10% of the reinforced concrete surveyed buildings collapsed. The more severe damage grades were mainly recorded actually in building design with the obsolete or absent seismic codes. The confined masonry is the most common structural typology among the masonry buildings. 22% of them has collapsed, and only one hospital was made of wood with light infills and 2 with stone infills, which has collapsed. They were far away from the main epicenter, suggesting that they were either poorly designed or already in a very poor condition. So the next slide shows very minor damage that has been observed in reinforced concrete buildings, especially in cases of engineered structures with respect to minimum design principles and newly designed structures with actually a very low seismic concept. And we can also observe that light roof structures have experienced or exhibited very low damage. As in the opposite side, in the next slide, we can observe that in the next slide, we can observe that the heavy roof may have attracted most of the seismic mass, causing damage, such as if we look at the severe damage example, the columns, there is severe damage between columns and beam columns joints, and this compromises their vertical carrying capacity. These buildings did not collapse, but it sustained the very severe structural damage in the second floor level. The collapse case actually show that in the ground floor, there is a completely loss of vertical loading capacity, carry capacity, leading to a collapse of that story. So this is one of the most common example of what we can call soft story collapse. So then on the next slide, we can observe two examples of masonry buildings, no damage of masonry buildings, where we can confirm that light roof has been beneficial for preventing seismic damage. And then the next slide brings us to some examples showing moderate damage to collapsed buildings. The most common damage mechanism observed in masonry buildings was the failure of infill walls due to the very poor connection between the structural and non-structural component, as we can observe also in the last example, for the collapse examples, that the poor connection has been observed also between the main frame and the foundation as well. So, and now should like to give the floor to Jacob, which is going to talk about the damage assessment for schools.
Thank you very much, and good evening, everyone. In the next few slides, I'll show you the preliminary results and damage assessment for the schools in Haiti. So as you can see from the slide and what Luigi stated earlier, 836 schools were assessed by the team. From the map shown, you can see that the severe damage and collapse of the schools followed the line of the fault, highlighted in pink, and these being the orange and red dots respectively. So on the next slide, it can be seen that in terms of typology, 40% of the schools were confined masonry and 26 were concrete frame with masonry infill. Conversely, only 3 and 4% were schools with wood light frame and wood with stone infill. And these tended to be non-engineered structures using local materials and expertise. So in terms of damage level, it was promising to see that 39 and 25% of the schools experienced minor and no damage respectively. However, 93 of the total schools were severely damaged and 51 experienced partial or total collapse. So running through the different typologies on the next slide, it can be seen that wood light frames performed the best, with no schools collapsing and the majority of them experiencing no or minor damage. So these tended to be very simple brace frame structures, as soon as the image in the top right. So this school in particular is within 5 kilometers of the fault and experienced no structural damage. Surprisingly, the unreinforced masonry structures had the highest percentage of schools experiencing minor damage. However, this was mainly attributed to the small accelerations and the seismic force experienced further away from the fault. These were mainly situated along the northwest and south coasts. Other typologies such as concrete frame and confined masonry structures, despite still having 42 and 36% of schools experiencing minor damage, tend to have poor workmanship and connection design. Schools constructed out of wood with stone infill performed the poorest, with 48 and 16% of schools experiencing severe damage or collapse respectively. Typically, these had little or no connection between the wood columns and the stone infill, thus the stones fell out. The wooden posts were also locally sourced, not straight, so without any lateral support, it tended to collapse, as seen in the bottom right image. So on the next slide, damage patterns and lessons learned. So similar to those described by Alessandra for the hospitals, common damage patterns experienced for the schools included in-plane failure, out-of-plane failure, and typical X-shaped cracks and poor connections. So where reinforcement was evident, this was typically poorly designed and had a weak interaction with the surrounding concrete or masonry. And whilst concrete material quality was an issue, this actually played a lesser part in those schools that experienced severe damage or collapse than poor structural form and detailing. Deficient construction practice was evident, particularly where openings had not been thought through. So on occasion, bricks have been left out of the walls to provide ventilation. However, the subsequent seismic force from the roof above had no clear load path to the shear wall below. Next slide. On the other hand, the majority of schools did perform well in the earthquake, and these tended to be simple structures with regular plan and adequate strength and ductility. As alluded to earlier, light timber roof structures performed extremely well, experiencing little or no damage. Where there's sufficient connections, these schools also performed effectively. Schools which had strong foundations also performed well, regardless of typology, and the schools where the floor level was stepped up above the ground performed the best, as seen in the top right image. Well-designed confined masonry structures perform best closest to the fault, as you can see in the bottom right image. This school in particular was built with the aid of the NGO Build On, which provided 26 of the assessed schools. This takes me on to the following case study. So despite the failures in those schools that experienced extensive damage, a number of case studies were found which bring to light the current efforts to provide the required resilience to future earthquakes. As Tracy alluded to earlier, there was evidence of NGOs such as Build On and Build Change having provided aid and retrofitting to schools in Haiti following previous natural disasters, with the additional aim to provide education alongside so that local communities can assess the risks and design and build suitably sustainable structures. So how did these structures perform in the recent August earthquake? So 12 of the schools experienced minor damage, small hairline cracks as falling of plaster. A further 8 experienced moderate damage with large X-shaped in-plane shear cracks, with vertical cracks along the corners of the structure and horizontal cracks along the top of the walls and beams supporting the roof structure. Further 4 experienced severe damage. However, these were all within 2 kilometers of the fault. It was promising to see that no schools collapsed. However, only 2 schools experienced no damage at all. And damage was experienced in schools that were outside 10 kilometers from the fault, in Pestel in the north and Masalan and Anique in the south. Further collaboration with the other work streams will likely provide insights into the main causes of the damage. I will now pass you on to Francesco, who will talk to you about the churches. Sorry.
Thanks a lot, Jacob, and good evening, everyone. So following up on the discussion of the structural assessment, I'll be presenting here the damage level for a portfolio of 390 churches that were assessed, which represent more or less 46% of the total data set that we're gathering and uploading the forecast map. Here, presenting a general overview of the structure topology and the damage assessment for the whole data set. In the upper left, we can see that basically most of the churches were made of reinforced concrete and confined masonry, which are grouped in confined masonry, unreinforced bearing walls, and reinforced bearing walls. Together, reinforced concrete and masonry structure were more or less 87% of the total of the whole data set. Conversely, we have also 11% of the structure that were made with wood with the light frame and wood with stones. And finally, we have also added one other category, which is unknown, because in some cases were very difficult and the photos were not clear enough to identify the kind of structure topology. On the right, we can see the damage level for the whole data set, and then unfortunately we can see that 26% of the total churches had collapsed. They were very close to the main epicenter, while 27% of them both have experienced either severe damage or moderate damage. In the bottom, you can see also the map of all the buildings that collapse, and as you can see, there are 2 different aspects that we can say. Many of them have a collapse along the fault, which is also related to the kind of energy released by the earthquake and the kind of soil site amplification that we can find very close to the fault. In the next slide, we have also detailed some of the structure topology in terms of damage assessment. You can see reinforced concrete structures and have behaved better than confined masonry. We have, unfortunately, 60% of the total collapse for reinforced concrete structure and merely 32% for confined masonry. Same thing for unreinforced bearing walls and reinforced bearing walls. We have actually 30 and 33% of total collapse. And finally, we have wood with stone infills and wood with light frame. And basically here we have, for stone infills, we have 63% of them have collapsed compared to 5% of the total collapse for the wood with light frames. In the next slide, you will see a couple of examples of good design for reinforced concrete and masonry structures. You can see that regular plant, light roof, good connection, good material, and even following a seismic oriented design have also helped a lot in terms of performance during the earthquake. In the next slide, basically you can see some of the damage that has occurred during the earthquake for reinforced concrete structures. Basically, has been common for all across this kind of structure topology, the kind of damage that we have found for example, heavy roof, autoplane mechanism under the sign beams and columns, poor connection between structural components and infills, heavy stones that mainly have attracted a lot of seismic mass, causing a lot of collapse. In some cases, the poor connection also has, of course, induced a lot collapse of the reinforced concrete structure, as you can see in the upper right of the picture. And then in the next slide, you will see some of the example for masonry structures. Once again, we can see a lot of relevant damage in the structural capacity, even in the structure very close to the coastal, which were also affected not only by the earthquake, but from, in some cases, by the problem of corrosion. And you can see once again the autoplane failure mechanism, which is common for this kind of buildings, the masonry buildings. And then here in the upper right, you can see, for example, the collapse of the structure, where we can see poor connection between structural components and foundation, and poor connection between structural component and infill walls, and finally poor handmade materials. In the next slide, you can see also the differences in the comparison between wood with heavy stones and with the light frames. In the first case, with the heavy stones, you can see that basically heavy stones have carried a lot of masses and then bringing the structure down after the earthquake, while conversely, the wood with light frames have behaved much better than the first ones, due, for example, to the lighting fields and due to the lighting fields compared to the first one. And with this one, I'll hand it over to Kajan and Bobine for the housing part. Thank you.
Thank you, Francesco. Haitian houses are known for their wide range of unique and artistic styles. Next, please. The first typology is wood light frames. You can see from the pictures, this includes those made from wood pole frame metal with a light metal roof. Also, some are made from reclaimed sheet metal or wood panel cladding and may have thatched roofs. They are lightweight and cheap, and issues with deterioration related to weathering might make them vulnerable. Next, please. Clissage classification is the most popular in rural southern Haiti. It's a wood frame typically with small stone infill or clissage wedel and daub. There are various types varying by stone size, thickness of the plaster, framing quality, or post type. Next. Other types include braced, part clissage weave, part infill, hybrid mixed concrete column, and wood frame. We observed issues related to insect attack, weathering, especially moisture, and implementation, including due to the hybridization of the system. Next. The other typologies are concrete frame systems and confined, unconfined, and reinforced masonry bearing wall buildings. Often they have the same type of roof and similar connection issues. Next. The map shows the locations of our damage assessments. We mainly focused on the epicentral area Lazille and Lekai. Based on random assessments, almost half of the data set was wood frame with stone infill and a quarter confined masonry. Next. Based on our initial assessments, damage distribution doesn't follow an exact pattern. It's clear this is complex. It can be said that the quality and implementation of construction had a role in damage, and no direct correlation was found between the damage and epicentral distance. Next. Here are some damage statistics. We did 890 damage assessments. There are clear differences between typologies. 25% of confined masonry buildings are classified as partial or total collapse, and 16% as severe damage. On the other hand, for clissage classification, collapse was assigned to only 8%, and severe damage was found for 36%. And much less damage was found for wood light frames and concrete frame buildings. Next, please. Here are some damage examples. Light roofs are very beneficial. In cases with heavy damage to walls, the roof doesn't tend to collapse. On the other hand, inadequate framing and loss of infill appear as bad aspects. An advantage of small stone infill without heavy plaster is that it will possibly cause less injury when it falls as small pieces. Plastered block infill might more likely fall as one wall, and bracing systems seem to have less severe damage, especially if bracing is used for all panels. Next, please. An interesting feature is the use of concrete porch columns tied to a wood frame. For these hybrid structures, there is an imbalance of stiffness, which probably influences and increases damage. It's noted that many porches introduce layout issues with a re-entrant corner. And another advantage of glissage light roof buildings is that they can be quickly converted to shelter by using sheeting and readily repaired. And thank you. I'll now hand over to Mobin to talk about multi-story structures and provide recommendations.
Thank you. For multi-story buildings, many instances of pancake collapse and soft story failures were found. Pancake collapse was one reason for the large death toll in 2010. Here, there are fewer of these structures, and this may be one reason for the lower death toll. The usual suspects were found. Issues included heavy roof and floor slabs, low quality concrete, and the failure to adhere to recognized seismic guidelines. Some of these buildings were older, but some could have been built post-2010. Next slide. Recommendations. Good design guides and a newly implemented Code National de Bâtiment d'Haïti 2012 is available. Difficulties are access to knowledge, socioeconomic issues, lack of quality local materials, and lack of enforcement or compliance. For easier retrofit of glissage, one good solution is to use a backing board or mesh to ensure stone infill falls out rather than into the building. Use of bracing should be expanded and support extended for retrofit and replacement programs. I'll now pass over to Mike, who's going to provide concluding remarks.
Thank you very much. So one of the next steps that we're looking at as a team, and has been alluded to in the previous slides, is understanding the interplay between the earthquake itself and the building damage. Obviously, one of the aspects has been talked about is that it's difficult to discern the clear correlation between some of the damage observed. So the team is going to be looking at the interconnectivity between the fault movement and the fault aspects, and looking at seeing if we can understand in more detail some of the aspects. So we're working on a team to try to understand some of that in greater detail. So just to bring some concluding remarks and to bring some of the aspects together. So obviously we've identified that the earthquake was and the faulting is extremely complex, and that we need to understand the earthquake in more detail and understand the fault and the fault hazard within Haiti further. We've demonstrated that remote sensing, including INSAR and optical imagery, can be used to understand the impact of the earthquake and can provide automated detection and automated assessments on infrastructure, and can play a crucial part in our understanding of the earthquake and inform rapid assessments and mobilization. The work has identified that there's a range of issues linked to the typologies of buildings across from schools, houses, hospitals that the team have gone through in terms of building quality, building structures and building types. And there's a lot more work that needs to go in to understanding sort of the design philosophy, the construction methodology, supporting aspects like retrofit and work such as that. So without further ado, first of all, thank you to all the team that presented, and I'll open up the floor to questions. Thank you.
Thank you very much, Mike. That was amazing to get through so much in such a short space of time, and we've still got a little bit of time for questions. If I can remind everybody, please, you are able to post your questions here in the chat, and please encourage you to do so. So let's start with some questions on landslides. So these two will actually go to yourself, Mike. There's two here. Is manual mapping methods of landslides also a part of the mission objectives? That's from Adityan. And again from Adityan, how many landslides have been estimated to have been caused by the earthquake? Have they been mapped using high-res remote sensing data sets? That one's for you, Mike.
Yeah, so to answer the first question, right from the start, we identified as part of one of the mission objectives was to investigate the impact of landslides. It was known from the 2010 earthquake that there was a significant impact from those. There was over 10,000 mapped. So one of the key things was to look at, as part of this mission, the use of imagery and different methods to use that. So yeah, it was key to the objectives. We knew from evidence that we understood that they had quite significant impact. So to answer the second question in terms of how we assess that, we looked at basically two different methods. We looked at using basically optical imagery from Sentinel-2, which has an accuracy of 10 meters. So that has limitations on the sort of size of landslide that you can identify, about 100 meters squared typically. And what we were able to do was identify, rather than always individual landslides, we were able to identify landslide clusters. And then we basically have supplemented that with INSAR. So we're using a range of techniques, from mapping via the person individually to also trying to automate the system.
Great, thank you very much, Mike. Again, any follow-up questions, put them in the chat. Next one, let's take two questions about the building damage and typologies. So Luigi, if I could direct these questions to you. There's two here. So from Abdul Aziz, is there any construction drawing records from local authorities, maybe, to determine and assess the buildings? How did you convince the local authority to conduct the study? And also, how was the local authority's feedback regarding results of the study? And if I could just give you another question on building types as well. And you're welcome to delegate these questions, by the way, Luigi.
Yeah, sure, no worries.
But this one as well is building types are a bit confusing. How did you come up with them? This is from Yavuz. Choosing the type of building, do you have a structural engineer in your panel? Okay, over to you, Luigi.
Okay. Yes, thanks, Josh, and thanks for this very interesting question. I will start from the last two that I have more confidence in replying, because I've also discussed this with the team with the team that I was coordinating, Alessandro, Francesco, Mobin, Kojan, and Jasmine. First of all, it is not clear, at least also based on the data that we have access to from STEER, that was illustrated by Tracy. There were photos. In some cases we had multiple photos, but not very close because of the let's say the limitation in accessing. Where it was clear, as also a number of discussion, the presentation today, they were clearly identified. In other cases, they were unknown. So I would say that for most of them, we were able to identify the structure of type. Some of them are also identified from the exterior, but not for all. Yes, we had in our panel, we are mostly engineers. So we had, we have also performed this activity before. So there is a sort of previous confidence and also experience that we put in place. And of course, we also discussed through a number of meetings. This is a coordinated activity managed by Mike, myself, and other colleagues that have been coordinating this activity, and we have met regularly to get an agreement, at least in between us, of what was the type of damage that we should, how we should classify them, and that's why we also set the metrics. For the first two, I would say that I can also delegate to others, but my point is that it's very difficult. My experience, I know the area very well. I was there also for this earthquake, but on the Dominican Republic side, it's not very easy to access data. If they are built by donors, yes, you may have drawings, but if not, I'm not sure that they exist. But I will also ask my colleague to intervene. I don't know if Alessandro, Francesco, or Mobin or Kojan want to add more in this respect. For the accessibility to data, I don't know, Mobin, do you want to add something?
It's not something that we looked at in a great way. It's difficult to have access to that sort of data.
Yeah.
You will be able to find, so for certain types of houses, there is that sort of information. These are the ones that have been built by NGOs. And so for those NGO type houses, even things like experimental testing have been done to demonstrate their performance. But generally, no, that sort of information is not available. And the thing to remember is in terms of houses, in any way, they're built by the owners.
I do agree with Mobin, and as we said, it's very difficult. We have based our engineering, I mean, we filtered the data through our engineering judgment, and through common discussion, we ended up with this damage selection.
So Josh, I also thought Tracy might be able to provide some stuff on the feedback to the community on the housing and the surveys.
Yeah, so with respect to that aspect, it's actually interesting. We went in through STEER, but it was upon seeing that we could access areas that the government was still having a difficulty assessing that our involvement has continued to grow. So actually, not only were they aware of the effort, we're now expanding and piloting the effort as part of an extended assessment in the rural areas, which is an area where the current government-led efforts with UNOPS have run into some challenges. So I think there definitely is not only an awareness, but a possibility now to use this as a way to help reach some areas that were difficult to assess. With respect to, I think, was the other question just around the locality's participation or how we got local agents to collect data? I'm not sure which side the question was on.
It was both. So was there data from local authorities, and how did you convince the authorities to get involved? Basically, what was the involvement of the local authorities, and how did you convince them? What was their feedback?
Yes. Okay. So with respect to local authorities, we have mandate under the US government to deploy teams to then share data back with local authorities. So we collect the data and share it back. So I guess my point was that by us getting in there early, we actually started generating data that they could use in some of their official work. And so that's kind of how that unfolded. In terms of getting access, a lot of that was also coordinated through Geohazards International, which is already present in country and had those existing relationships, particularly in NEEP. I also was working through Catholic Relief Services in Sud, and we were there prior to the earthquake. So a lot of what we were able to do was actually working through non-governmental authorities that were already connected in the country to be able to get our efforts moving quickly to recruit individuals and to be able to share the information back and now be able to even extend that as part of the ongoing assessments in country.
Very good. And I think also, Yevuz, on your question, did you have a structural engineer on your panel? The EEFIT team is made up of, or the mission team is made up of those volunteers that put their name forward. So when the event occurred, EEFIT put out a call for expressions of interest. So anybody that would be interested to attend, including yourselves and those on the call, would then submit their names and their reasoning for wanting to be on the mission. And then we selected the team according to the different skill sets, etc. So the team was specifically chosen to have a good mix of skills there. Okay, well, we're nearing the end, but I'll go for one more question if that's okay. Where was it? From Law Falau, sorry if I'm saying that wrong. This is truly amazing! Exclamation mark. I mean, all what you were able to do together, I couldn't agree more. How challenging was it to coordinate all your efforts? I think this one is for Mike and Tracy. You have a huge team here and a huge amount of work that you've done over such a short time. How have you managed to coordinate that?
I'll let you go first, Tracy.
Yeah, our coordination was chaotic. So I am just super proud of the fact that people were willing to lean in and be graceful in operationalizing something we had never done before in terms of using local-led data collectors. So I would just say it was a commitment to have the story of this country be told and documented so engineers like these great folks could weigh in and contribute to learning from this event. So I just want to be humbled in saying we did our best. We worked nimble and there was a lot of blood, sweat, and tears put in to pull it off. And I'm super proud of those 50 data collectors. But then I'll kick it over to Mike because I love the way EEFIT sets up those work streams to get an amazing amount of high quality work done on the back end of our humble data collection. Mike?
Yeah, so I think I've also got closing remarks and sort of takeout. So I think one of the things I was going to say was sort of, first of all, really the amazing sort of effort of the community in Haiti that has fed into that. That's one of the really amazing takeaways that I've taken from it. But also sort of from an EEFIT thing going through from the very start of getting the committee on board to support the mission and then leading into this. And I've sort of really been humbled by the effort that people have gone to and the time given. You know, it's quite complex. People have got working lives and people have given up quite a lot of time to support this. So from that side of things, basically people made it pretty easy on my part because they gave up their time and they're quite committed. So, you know, it's just really setting up a nice structure to help them deliver that and giving them people the opportunity to talk. So yeah, so the things that I've took away from it was that main thing. of both the community in Haiti and the wider sort of community of EEFIT, steer, the likes of collaborating with GEAR, Map Action, and the collaborative nature of these sorts of efforts that bring people really from wide backgrounds together to support and try to learn from these events so that we can learn going forward and hopefully, you know, in essence, build a more resilient community to these sorts of hazards. And that's really my takeaway from, I guess, from our understanding of the earthquake. I think I've learned a lot more about the complexity of the tectonics of Haiti. You know, I think in terms of that side of things, there's a lot to do from understanding that. The amazing building typologies from churches, schools, all of that side has been quite a lot. It's very complex, and there's a lot to learn going forward of how we can basically improve building resilience. And also, I'm from being a remote sensing person, I'm also pleased that the output from the remote sensing actually can provide input to these sorts of things and help sort of more rapid assessments and rapid guidance to these events. So those are sort of my takeaways from the thing. So back to you, Josh.
Great, and I think that's a great set of closing remarks, and we're bang on time. So that just leaves me to say a huge thank you to Tracy for enabling this amazing collaboration to take place with Steer and EEFIT. This is our first one. I hope the first of many. It's really been great working with you guys. A big thank you to the team. Monumental effort. You've all got full-time jobs and plenty of other things to be doing, and you're giving all your time to doing this. A huge congratulations to Mike for bringing that all together, and a big thank you to the audience. I hope this has been of interest. Do get in touch if you'd like to be part of future missions, and please, everybody think about how we can use this information for good in the next event. Thank you very much, everybody. Take care.
Thank you.
Thank you. Bye-bye. Bye all.
Bye.
Bye, everyone.